We move on to the next speaker, Andrea Blanco-Redondo. She will give us a talk about topology as a degree of freedom for multiphoton entanglement. Andrea Blanco-Redondo is now the head of the Silicon Photonics department at Nokia Bell's lab in New Jersey. She got her PhD in the University of the Basque Country, and her research interests span across integrated photonics, nonlinear photonics, and topological photonics. So we are slightly moving on to the realm of photons. So Andrea, whenever you want, please.
Okay, thank you, David. Thank you very much. First of all, can you guys see my slides all right?
Yeah, we can.
Okay, perfect. Yeah, well, so thank you very much for this invitation. I'm really happy to have the chance to talk to the topological matter community, which, you know, is not something I do as often as I'd like. You know, I tend to talk more to the photonics community, so this is a real privilege for me. So today I'm going to tell you about the, you know, a series of experiments related to you know, topological effects in nanophotonics platforms, and in particular how topology can protect entangled photonic states, and how can we use topology as a new degree of freedom for multiphoton entanglement. So I'm going to talk about a series of things. So I wanted to start by thanking some of my collaborators. Lots of people have been involved in the research that I will talk about, but I would like to specifically recognize Bryn Bell, who's now at Imperial, and he worked really closely with me when we were both research fellows at the University of Sydney. Sorry, my slides are kind of like running automatically, so I don't really know how to stop that, but anyway. So Bryn worked really closely with me in defining the initial topological quantum experiments in photonic platforms, and I would also like to recognize Michelle and Cooper, who are two of my previous students that took some of the measurements that I'll show towards the end. Just a couple of words about where I work. I work for Nokia Bell Labs, and in particular, I work in the Bell Labs headquarters, which are in New Providence in New Jersey, only 35 minutes from Manhattan without traffic. And you know, even if Bell Labs is a much smaller place than it used to be decades ago, the culture that led to these very impressive inventions and discoveries still very much persists. So it's an interesting place to work at, and definitely an interesting place to visit as well. So if you ever are in the area, please just you know, shoot me an email, and I'll be happy to show you around. Now, as David said, I'm the head of the Silicon Photonics department, and I just wanted to point out that most of the things that my team does are actually not as fundamental as the thing I'm going to talk about today. We have a lot of people working in silicon photonics tunable lasers, modulators, passive devices, stuff that could have a short to medium term impact in networks and in optical networks, and also in data centers. But there's also a subset of us that are working in more fundamental long-term research related to topological photonics in silicon, and specifically as well as to see if we can contribute to protect quantum information in silicon photonic circuits. And also we have a lot of activity in nonlinear effects in integrated platforms as well. I'd like to point out that Bell Labs has a strong effort as well in topological quantum computing, using electronic ensembles. But I'm not going to discuss that there. If you're interested, the main person there is Bob Willett and Gerardo Gámez as well. All right, so topology in photonic systems manifests in the bands of the dispersion relation of the optical spectrum, right? So what I'm showing you here in these slides is an image of the first experiment that was done by the MIT group, in which they demonstrated experimentally the first topological effects in an optical system. And it was done at microwave frequencies. So what you're seeing here is basically a photonic crystal made out of ferromagnetic materials that basically, when you apply a strong perpendicular magnetic field, behaves like basically like an analogy to the quantum Hall effect, right? So what you can see here, for example, in the optical spectrum versus momentum, is that the bands acquire different Chern numbers. That's the relevant topological invariant here. And what's interesting is that at the interface of this topological material with a metal, what you can see is that you can excite these edge modes that propagate on the edge, protected against any scattering into the bulk. And even when you introduce very large defects, as you can see here, the electromagnetic modes are capable of going around the defect and propagate without scattering into the bulk. So when this came out, the photonics community got really excited because we saw this as basically an opportunity to overcome some of the important problems of photonic integration, which are related precisely to backscattering due to errors, fabrication imperfections, and environmental changes. Now, the problem with this particular implementation is that it requires a magnetic field. So it's okay to work with microwaves, but the magnetic response of optical materials, the magnetic response of materials at optical frequencies is actually tiny. So if we want to bring these towards the near infrared and the visible, which are like the most interesting areas of application, we need to come up with something else, right? So the community started thinking about it. And what I'm showing you here is the first structure used to demonstrate a topological insulator at optical frequencies. And this is done by a group at the Technion. So basically the idea here is, okay, so if we cannot use a magnetic field to break the time reversal symmetry, how about we create an analogy to this by breaking the Z reversal symmetry, right? So that's what they did with this array of helical waveguides. The idea here is that if we had an array of straight waveguides, our optical spectrum would look like this. It would be gapless. But when we introduce the helicity, basically a topological bandgap opens. And what's more interesting, there are two gapless stages crossing the bandgap, propagating in opposite directions, one localized in the top edge and the other one localized in the bottom edge, right? So this is basically the idea. When you inject light in one of these waveguides, it would propagate basically in a kind of like inside the plane, inside your screen, but at the same time, these waveguides are close enough so that light can couple from one to each other. So let me just show you a simulation from this group at the Technion. So what happens is if you inject light in this waveguide here, it will propagate coupling from waveguide to waveguide all the way to reach this corner here. And as you can see, it will propagate around the corner, which is a pretty huge defect, without backscattering into the bulk. So this was obviously a very interesting breakthrough, but this particular type of 3D structures are not I guess the most practical for basically solving the problems of photonics integration. So shortly after that experimental demonstration, there was another experimental demonstration by Mohammed Hafezi's group in Maryland, which basically was based on this coupled array of coupled micro-ring resonators, as you can see here. And what they do is basically they tune the coupling phase in between the different rows of this lattice. And what this achieves is that basically a photon propagating in this direction, if you follow the red trajectory here, acquires a positive phase, and a photon propagating in the opposite direction acquires a phase in the, sorry, that's what we should be following here, the dashed line, acquires a phase that is opposite in sign, right? So in this way, they create this synthetic magnetic field, and again, they're able to generate these gapless stages that propagate around the edges of this lattice with certain protection, with protection to certain types of defect. Another option, also in a planar structure and also implemented experimentally by the group of Mohammed Hafezi, is this idea of using a two-dimensional photonic crystal in which basically the main cell is either shrunk or expanded. So while we do that, the shrunken structure and the expanded structure that you can see here by this triangle, which are, let me just explain a little bit how this looks like. So this is I believe this is a gallium arsenide membrane, and the triangles are basically air perforations on them. So the idea is that when we take the triangles away from the center, that's the expanded structure, and that acquires a different topological invariant than the shrunken structure. And what they demonstrated is that photons with different chirality coupled to opposite unidirectional propagating modes, and therefore photons of one chirality would propagate in one sense, and photons with the opposite chirality would propagate in the other direction. All right, so this is as for 2D photonic structures. But there's a lot done as well in exploring one-dimensional symmetries in photonics, including the stuff that I will tell you about and the kind of structures that we've been focusing on in my group. Many of these one-dimensional structures are based on the SSH model that I will discuss further in a minute, but I'm sure all of you are very familiar with. So the idea basically is alternating the coupling strength between sites. And at the interface, basically between two mirror images of this SSH lattice, you can get very strong localization that is topologically protected with respect to offside disorder, to off-diagonal disorder, so disorder in the coupling strengths. And it can be implemented in many ways. Obviously, it was discovered it was studied for the first time in polyacetylene chains, but it's been implemented in optics in a variety of platforms, including resonators and silicon photonics waveguides, which is what I will be talking about today. And then there have been other studies of topological photonic structures in one dimension using, for example, quasi-crystals or zigzag chains that lead to related effects, not exactly the same as the SSH, but related effects like you can see here, for example, this strong localization here. All right, so let me talk a little bit about this topological platform that we've been using for both our classical and our quantum optics topological experiments. So as I said, our platform is based in the SSH model, investigated for the first time by Su, Schrieffer, and Heger in 1979. And the idea here is we have a series of silicon photonic waveguides, and these waveguides are very conventional. This is the type of widths and heights that are used in silicon photonic chips that are used commercially. So what we do is basically we alternate the gaps between waveguides. So we use a short gap followed by a long gap between them, and that way we create that alternate strong and weak coupling between waveguides. What we do at the center of the lattice is we create what we call the long defect, which is basically two long gaps next to each other. And what this creates is basically it creates a topological transition between the lattice on the right that we have shaded yellow to represent that it has a Zag invariant, a Zag phase of pi, and the lattice on the left that has a Zag phase of 0. So as you well know, whenever we have a topological transition, we have a localization of a mode there that is going to have certain topological properties. So to illustrate this a little better, I wanted to compare it to a system that may be more familiar for some people, which is just having an array of equidistant coupled waveguides, just like that. This doesn't have any, special fancy symmetry here, rather than all the waveguides are equidistant from each other. So if we plot what would be the equivalent of the optical spectrum here, or the energy spectrum, which in this case is embodied by, instead of having the frequency, the optical frequency, the temporal frequency in the y-axis, we have the spatial frequency, or in other words, the propagation constant of each of the supermodes in the lattice in the y-axis, and we just have the mode number on the x-axis. So what I wanted to show you is when we have an array of equidistant waveguides, we have a gapless spectrum, but as we start dimerizing the system, as we start creating that alternate strong and weak coupling, as you can see here, a topological bandgap opens. And because of this long defect that we leave in the center here, then this mode appears here in the middle of the bandgap, which is strongly localized, and it remains pinned at the same propagation constant. Now, what's interesting about this lattice is what happens when we introduce disorder in the system, right? So even just by the pure nanofabrication processes, systems have disorder of the order of a few nanometers because of the fabrication techniques, right? So if we think of moving the waveguides around, right, like randomizing the position of the waveguides, or in other words, randomizing the width of the gaps, what's going to happen is that all of our extended modes are are going to have propagation constants that change. Therefore, if we were to couple to this mode, the phase of the mode at the end would be different in each of these iterations. However, the propagation constant of the topological defect mode remains pinned at the same value, even in the presence of this type of disorder. Okay, so this is something we will try to leverage in our quantum experiments. Now, initially, we just studied this from a classical point of view. So we just pumped these lattices with a continuous wave laser, and we measured the stuff at the output, both using near-infrared images and also power measurements. So what you can see here in the case of the topological lattice is, first of all, there's a strong localization towards basically the center waveguide. So if we input here in the center waveguide of the lattice, we're going to excite the topological mode quite efficiently, and therefore our light is going to remain localized there. So you can see this exponential localization here, but more importantly, you can see this kind of like very strong zigzag pattern in which your amplitude, or your power in this case, is localized in only one of the two sublattices, whereas the other sublattice has theoretically at least zero power or zero amplitude. In this case, in the experiments, we had a tiny bit amount of power there, but just related to the fact that there's also a tiny bit of residual coupling to the other extended modes in the lattice. Now, again, for comparison reasons, this is what would happen if you pump an array of equidistant waveguides in the input. Basically, no localization. Your mode would actually spread out in the waveguide following something called discrete diffraction. So nothing too special there. Now, what's interesting about silicon is that we can also allow for the generation of correlated photons and entangled photons using the platform itself. They can be generated on chips. So once we did these experiments, the first thing that came to mind is, how about we study if this structure can also protect certain quantum properties of quantum states of light. So just like us, other groups as well had similar ideas on their own platforms. And what I did in 2020, if you're ever interested, is basically I compile the experiments that have been done in terms of topological protection of photonic quantum states. And this is basically a table summarizing all that. I'm not going to go through all these. I just wanted to let you know that this is available if you're interested. But I'll just say a few words. Different platforms have been used to study topological protection of quantum states. This is ours, but then also you have Hafezi's structures here as well. But I think what's more interesting is what are we talking about when we are saying that we can topologically protect quantum states? Well, that's extremely dependent on the system. For example, in these experiments here, they looked at robust spectral correlations. So that means if we are generating photon pairs that are correlated in frequency or entangled in frequency, are they always going to be at the same frequencies, even if our system is not perfect and have imperfections? So that's one way to look at things. What we're looking at is topological protection of path-entanglement. So this is related to, can topology protect the amplitude and phase relation between different components of spatial entanglement? And then other people, as the group of Xiaoming Jin in China, are looking at protection of polarization entanglement. All right, so I'm just going to start talking now about how we started doing quantum experiments in this platform. And the first thing we looked at is the topological protection of biphoton states. So as I briefly mentioned, the beauty of silicon is that it allows you to generate correlated photon pairs on chip. Now, how do we do this? Well, if you pump the system with a relatively intense laser, and in this case, we used a pulse laser, a mode lock laser, you can take advantage of a Chi3 nonlinear effect in silicon, which is called 4-wave mixing. And this is also enabled by the fact that these nanowires have a very strong confinement. So therefore, the intensity of the light is very large. So via this 4-wave mixing, this is a nonlinear effect that allows you to basically annihilate two photons the pump frequency and give rise to a signal and annihilar photons in a process that preserve energy and momentum conservation, right? So because of that, we know that signal and annihilar are correlated in frequency or entangled in frequency, but we also know that they were generated exactly at the same time because the Kerr effect, this Chi-3 nonlinearity is instantaneous. Now, we could pump the system in principle in any of the waveguides, but we decided to pump on the center. So we expect these biphotons to couple strongly to the topological mode. And what we do here at the output is basically we spectrally separate signal and annihilar because there are different frequencies. And then we detect them individually with superconducting nanowire single photon detectors. And we basically look for time correlations between them, for coincidence between them. So what we get at the output is what we call the biphoton correlation map, and I'm showing this here. So basically what these have is the position of signal annihilar, correlated signal annihilar, in an interval of 2 minutes that we were measuring. And this is these indexes here represent the waveguide index. So what you can see here, first of all, is in the absence of deliberately introduced disorder, most of our photon pairs, most of our correlated signal annihilers are in the center waveguide number 0. But we also have the presence of, some photon pairs also in other waveguides. But what is interesting, and again, let's relate this to the underlying SSH model, is that we have 0 counts in one of the sublattices, as you can see here. Now, what happens when we introduce disorder in this lattice? Well, we can do that by, as I mentioned before, randomizing the position of the waveguides or randomizing the gaps between waveguides. And this percent number here basically is telling you what is the equivalent maximum variation of the coupling constant between waveguides, right? So when you vary things up to a 20%, you can see that, sure, things in one of the the correlated counts in one of the sublattices can change, but this signature of the topological mode, the underlying topological mode, remains really strong with these 0 counts in one of the sublattices, and that's basically maintained also for very large levels of disorder. So just to remind you what's happening underneath, we have this SSH lattice, which basically, these are simulations here, in the absence of disorder, you would have a mode like what's represented by the black markers. When we start increasing these different levels of disorder in the coupling constant, the amplitude in this sublattice can change, but we are expecting the amplitude in the other sublattice to remain strongly pinned at 0. But what's more important is what happens with the propagation constant or the quasi-energy of this topological mode. Well, as we increase the level of disorder, we see that the gap starts to close, the topological gap starts to close because that dimerization starts to change. But we can see that the propagation constants remains unchanged. In this case, it's normalized to 0, but it's not really 0. It's just a fixed value here. Now, for comparison, and just to demonstrate that there's something special about this structure, what we did is we generated an array of equidistant coupled waveguides, but we generated localization using a trivial type of localization, which doesn't have to do with topology at all, which basically relies on making just one wider waveguide, as you can see here. And that leads to exponential localization as well. But as I said, this localization is of trivial nature. So when you perform the same type of measurements at the output, what you have in the absence of disorder is just a given pattern, also with most of your correlated signal annihilar photons being in the center waveguide. But as you increase the level of disorder, there's no spatial feature that is protected at all. Now, if you look at the underlying trivially localized mode, you can see that indeed no protection against disorder was expected here. There's no feature preserved here. And what's more important, the propagation constant of this localized mode is also supposed to change with disorder. So that was the first experiment in which we observed topological protection of biphoton states. And it was the protection of certain features of the biphoton correlation. spatial biphoton correlation. Now, we started wondering, okay, how can we truly use this, right? Because in this case, all our photons are in the same spatial mode. So what does it give us to have a spatial protection? Well, so what we did is said, okay, well, let's expand this and take advantage of that spatial protection by creating basically spatial entanglement or path entanglement. So this is what you see here in this experiment. You can see basically that we have the same type of lattice, SSH lattice, but in this case, we have two long defects. This one here in 107 and this one here at 96, okay? So by employing a similar type of pulse laser and basically a beam splitter here, we can encode a NUN state, which is basically a superposition of your signal annihilator being in mode A or your signal annihilator being in mode B. Right? If you're interested in how we generate this entangled state, I can refer you to this paper here by the Bristol group. But the idea is that you know, we want to probe the entanglement between these two modes at the output and see if it's robust at all to disorder. Okay. So these measurements that were taken by my students, Michelle and Cooper, look exactly like this. So this is the experiment here, and this is the simulation here. And notice that we measure many of these. I'm only showing you one case, and I've decided to show you the most challenging case, one of the highest levels of disorder that we measured. So this is 40% deliberately introduced disorder. And what you can see here, well, first thing is that your biphoton correlation does look like an entangled state, like a NUN state, in the sense that you have your signal annihilator, both of them either in mode A or in mode B. You don't have cross terms here. And the second thing that you can look at is, again, these zero counts in one of the sublattices. Now, for comparison, we did exactly the same thing with one of these waveguides, with one of these lattices in which we introduced basically wider waveguides. So we created two of these type of defects, and we encoded an NUN state across those two trivial defect modes. And what we measure at the output, and notice that here I'm showing you 0% deliberately introduced disorder. So this is just basically the inherent nanofabrication disorder that we can't get rid of. What you can see, first of all, is you know, we do have some type of NUN state. We don't have cross terms here either. But the modes already look very different from each other, and they look nothing like the simulations, right? So again, this was expected. No protection is expected here. Now, to truly probe the robustness of that path entanglement, one needs to do quantum interference. Now, we actually didn't do this experimentally, but I can show you some simulations of how this would work. Basically, the idea here is that, you know, at the output of your lattice, you have that NUN state we were discussing, and notice this phase term here. If your mode A and your mode B have exactly the same propagation constant, then this phase term should be this phi should be 0, but this phase term should be 1. So it basically should disappear. And then what you can do is you can just basically take these two modes to an interferometer. So you can think of this as basically a reverse Hongo-Mandel interferometry. And at the output, in principle, you have two options. Your photons can be bunched, or if your photons can be split. So you have a superposition of these two options. And again, if your phase term is 0, if the difference in the phase between the two modes is 0, what happens is that basically you're always going to have your photons split. You can characterize the visibility of this interference. And again, if the phase term is 0, your visibility is going to be 1, which is ideal. So what we did is we calculated the mean deviation of the visibility. So how much things deviate from the ideal visibility in the presence of disorder. And we did this for the system with spatially entangled topological modes and the spatially entangled non-topological or trivial modes, right? So we can see that whereas the topological mode remains at a very good visibility, so therefore the visibility doesn't change much even for higher levels of disorder. In the trivial case, the visibility degrades extremely, it degrades a lot even for relatively low levels of disorder in the coupling constant. So it looks like topology does have chances of protecting, or does have a lot of potential for protecting quantum state, multiphoton entangled states in silicon platforms. And now the last thing I want to tell you about, if I still have a couple of minutes, is the lattice experiment that we have done, and these are unpublished measurements, but I'm hoping that we'll be able to post this in the archive in the next few days. The idea is that these type of lattices are actually very versatile, and you can design things pretty much as you want and send them for fabrication and test a variety of things. So what we did here, for example, is it's still based on the same SSH lattice, but now we basically engineer the interface to be a little different, and we don't have a long defect anymore. We have a short defect now, right? So we're still going to have a topological transition between lattices with two different topological invariant, and that's what you see here. So we have a bandgap that opens up and this topological mode in the center. But now, because you have three waveguides that are closer together, so therefore this region here has a higher index of refraction than the rest of the lattice. We also have trivial localization of these two modes here. We can see these smaller bandgaps that open up here at the lowest and highest level of quasi-energy. And what's interesting when we look at the modal amplitude of these modes across the different waveguides is that they're actually all of them localized in the center, but they have different modal amplitudes. Actually, the two trivial modes they would have the same kind of intensity pattern, but they have a different phase pattern. So they are not exactly the same modal amplitude. And then the topological amplitude looks completely different. And again, this time, instead of having a maximum at the center, we're going to have two maxima in the two waveguide -1 and +1, but we still have these 0 counts every other waveguide. Now, what's interesting, if we pump the lattice at the center, we excite only the two trivial modes, and we excite a beating pattern, as you can see here. But again, because of the same nonlinear four-wave mixing effect that we were talking about, what you have is that when the pump propagates through the lattice, imagine the pump is here, and your stochastic generation of photon pairs occurs here. So it can therefore couple to the topological or the trivial modes. And that's what we see here. We see basically that our photon pairs can couple to either of the three modes. Now, if you look at how things look, how the entangled state or the biphoton correlation would look at different points of the lattice, it obviously takes different shapes. And what's interesting is when you basically look at where are your signal annihilator photons? Are they in the topological mode? Are they in the trivial modes? What you can see is we start with all our photons in the trivial modes, but as we propagate through the structures, we end up with more and more photons in the topological mode. I think I'm running out of time, so I'm just going to quickly show you the measurements. These are experiments, these are simulations, again, for different levels of disorder. So what we observed is that for low levels of disorder, things behave pretty much the same with some discrepancy here, but at high levels of disorder, things change. Therefore, this system is not topologically protected. Again, this was not expected because the entangled state across the three modes has a strong component from the trivial modes. What's happening here basically is that whereas your topological state is preserved against disorder, your trivial modes aren't. And indeed, at some high level of disorder, we have new trivial states that come up and contribute to your entangled states. That's why things change so much for high levels of disorder. And just the last thing that I'll mention is if you look at the probability of population of the biphotons in different modes, what you can see is that even if we start with most of your biphotons populating the trivial states and not so many in the topological state, the topological modes remains quite robust to disorder, whereas the trivial ones decay really strongly. So for large levels of disorder, your entangled state will have much more of a higher weight in the topological mode. And that's it. That's all from me. These are my conclusions, and I'll be happy to take questions.
Thank you very much, Andrea. We stop on the questions, but maybe we have still time for some questions. You can raise your hand or post your question in the question and answer chats before we go to the colloquium. Do we have any question? I do actually have questions.
Awesome.
I have actually many questions, so maybe we can discuss them in the colloquium. But this platform, it's really fantastic. Congratulations, because it really shows that you have protection and in a realistic system. So the thing is working. It sounds like it could be applied to boson sampling, for example, no? Where we need to protect errors, and in that I'm thinking on for example, many protected waveguides. So my question is, how many layers do you need to build up the topological protection? Have you analyzed that? So do you need many, or with few you build up the protection?
With layers, do you mean waveguides in this case?
At both sides, no? So I guess you need.
Yeah. So how many? Yeah. So how many waveguides would you need at both sides of the defect? I don't know if I can give you an exact number. I can give you an order of magnitude. Probably 10 waveguides or so is enough to observe, in practical terms, good protection. What's important here is how efficiently are you coupling to your topological modes, right? Because if you're coupling to modes that are not fully localized, which, you know, it always happens because you have a lot of extended modes, then those extended modes are just going to reach the edges of the lattice or the other defects, the other topological defects, and eventually they're going to come back to you, kind of like polluting your sample, right? So that the more waveguides you add, the less chances you have for it to come back. But then again, it's just a trade-off. So if your waveguide is if your lattice is very, very long, you'll need more waveguides so that doesn't happen.
And also, have you considered to apply this system to boson sampling? So to include many more photons in the experiment? That would be probably challenging, but I don't know if the technology it's there.
Yeah, I mean, we have considered that as a potential possibility. The thing is that we've been kind of, okay, so the main limitation of this lattice, and I think I want to be really clear about it, is that it doesn't truly, it's not truly non-reciprocal, right? As you know, right? So it doesn't really protect you from backscattering, and basically the main source of backscattering in these waveguides is basically surface roughness, right? On the nanofabrication on the walls of the waveguides. So it doesn't truly solve the problem of larger scale optical integration, right? So the thing that you can truly leverage is basically the fact that the modes are have the same propagation constant, and therefore they're going to maintain the phase relation between them. So that's why we focus more on this, you know, multiphoton path entanglement rather than the boson sampling. But yeah.
Very good. I think we are just on time to go to the different separated meeting rooms. We have 3. You have already the links there in the chats. We need to get out from here, and then we will meet there. So you can ask questions to the speakers directly. Thanks a lot for all the speakers, and we are done with the session. Thank you very much.
Thank you.